Hello students, am I audible?
Yes, sir, you are
Yes,
audible.
sir.
Yes, sir, you're audible.
Yes, sir.
Yes, sir.
Is the screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, now tell me, your chat box is enabled or not?
It's enabled.
Yes,
Yes,
sir, it
sir.
is enabled.
Yes, sir, it's enabled now.
Okay. So now, today, we will start this, the very first chapter you can say of the fluid mechanics. What we have discussed in the last class was the introduction, introduction of that subject, this subject's fluid mechanics basically. And now we are going to start the very first chapter of this fluid mechanics, which is the fluid properties basically. Now, so in this our lecture, we will go with this like the introduction, then definition like fluid, then continuum concepts. Yes, the continuum concepts we will discuss, and then fluid properties. So there are different fluid properties basically. So we will look into the fluid properties one by one, and that fluid properties will come frequently in this subject basically. Okay, in this fluid mechanics. So that will be very important. So now, first of all, the fluid mechanics that actually we have already discussed. So these are the same things. Okay, so I'm not going to repeat this basically. As we have already discussed, that the fluid mechanics, the science, which deals with the action of forces of fluid at rest and motion, and there are this fluid mechanics is further divided into statics parts, kinematics part, and then fluid dynamics part. So that we have actually covered. So I'm skipping this actually. So fluid basically that we have also completed in the last lecture. These are the same things. Okay. If you will go with these slides, you will find that these are the same things which we have already completed in the last lectures. So again, and also that difference. Okay. So few slides of this fluid properties is same basically because we have already we have briefly discussed that fluid properties part in the last class. So these are that briefly part actually. Okay, now from here we are going to start basically. Okay, the properties of the fluid basically. So what are the different properties which plays the significant role in the fluid? Is that the first is the mass density. Then comes another one, that is the specific weight. Then comes the specific volume. Then comes a specific gravity. Then viscosity, surface tension, vapor pressure, capillarity, compressibility, and then bulk modulus. Okay, both are the related. Compressibility and bulk modulus are related. Okay. So generally both are written under the same topic. Now let me start these properties, all these properties, okay, one by one here. So first of all, what is the mass density? I think all of you are familiar what is this density basically. It is mass per unit volume. Okay, so that's the same thing. And we know that like water has a density of 1000 kg per meter cube, but it is at 4 degrees Celsius. If you increase the density, that increase the temperature, that density also decreases. And 1.2 kg per meter cube for air, which is at the standard condition like 20 degrees Celsius, and standard pressure means the atmospheric pressure like this. Okay. So this is our equation for the density. That D indicates basically the density. Okay. This is the density. This is the mass and this is the volume. Okay. So this is basically our density that we all are familiar. Now, yes, this second one. So the ratio between the weight. Here I think this is wrong actually. It should be or, not if. Okay, this is wrong. So it is the ratio between the weight of a fluid to its volume. So mathematically, if you will calculate this, actually, let me express this line in the terms of mathematics. Okay, so that is, let me take this gamma. So what is the weight? So let us denote weight with W. Okay, to its volume. So how we express this weight? It is mass into acceleration due to gravity. Okay, then we can further express this mass as a density into volume, that is rho into V into Z divided by V, where this V is the volume, this V is the volume, this V is the volume, this V is the volume. So that volume and volume will be cancelled out. So ultimately you will come out with rho Z. So this is here, you can see here the equation that a specific weight is, it means mathematically the specific weight is equal to density into gravitational force, gravitational acceleration. Okay, so this is our specific weight. So it is also called like weight per unit volume, and unit is like Newton per meter cube. If you will put the unit of this density and G will come out with this. So water, like the specific weight of the water is like 9.79. Means the extended, at the extended condition, you can say, like here if you put the gravitational constant like 9.81 into the standard density of water is like this 997 kg per meter cube. So when you will multiply, almost you will come out with this like this. Okay. So this is the standard value of a specific weight, 9.79 kilo Newton. This is was your specific. And now then comes another property, that is a specific volume. So a specific volume is defined as the volume of a fluid occupied by a unit mass, or a volume per unit mass of a fluid. So mathematically, how we can express this? That volume is this, like this V volume. Okay, it is defined as the volume. So we have to take the volume per unit mass. So you can see here it is just like the inverse of this density, because we know that density is like mass per unit volume. Okay, so it is just like the inverse of the density. So a specific volume, you can write down that volume of the fluid divided mass of the fluid. So it will be just the reverse of this density. So that is your specific volume. Volume per unit mass in a simple line, in a just in a single sentence. Now next come the specific gravity. Okay, so specific gravity here, let me first tell you, we have some standard fluid, a standard fluid. Like in the liquid, a standard is water, and in gas, a standard fluid is air. Okay, so these two is considered as a standard fluid. Okay, water in the liquid medium, air in the gas medium. So that standard fluid is going to utilize in the definition of a specific gravity. Now let us move to the definition of this specific gravity. The ratio of a specific weight. Okay, here you need to concern the ratio of a specific weight. Now move to the previous slides. What is the equation for the specific weight? It is rho z. Okay, so now the ratio here, you can take the specific gravity like this. So that is rho g. So this is for any fluid, any random fluid. Like here, you can see here your fluid is mercury. Okay. Now, here you can see the ratio of a specific weight of a given liquid. Given liquid means any liquid, okay, to the specific weight of water at a standard reference temperature, that is 4 degree, is defined as the specific gravity. It means we need to take the ratio if with respect to any standard, not any, it is generally water. So here it will be like H2O. Okay, now this a specific weight is for the standard fluid. Here it can be H2O or water, but generally in the fluid mechanics we will find water basically. Okay. Maybe in some if you are using like other gases, then sometimes it is used air also. Okay, but mostly you will find the water basically. So sometimes in definition you will find there is water. Okay, but it is basically a standard fluid. You can say the standard fluid with reference to a standard fluid. What is the specific weight of any fluid with a standard fluid? So if you are taking the mercury, means the specific gravity of mercury, then we have to take this rho z for mercury, then divided by, you have to consider this part like this. So this is your specific gravity. Okay. So now you can put the value of this here. Actually, this g is actually constant. If you are doing this, if you are measuring the specific gravity in the same gravitational field, then that g is basically will act as a constant, and this will be cancelled out. Okay. So ultimately, you will come out like density of the mercury. If you are taking mercury as your fluid, then it will be just like the ratio of density. The ratio between the density. Okay, so it's very simple. So you can just put here, actually the specific gravity of mercury comes out like 13.6. Okay, that specific gravity is unitless, remember, because it is a specific weight, it is a specific weight, so there is no unit of specific gravity. So that value comes generally 13.6 around, because you can see, you can check here 9.81, when you will divide, it will almost come out like 13.6, like this value. Okay, it will come out approx 13.6. So the specific gravity of mercury is 13.6. It actually, that gravity, that mercury is generally used in the numerical problem. So that value 13.6 is actually itself a standard value, because mercury is also a standard fluid actually in some cases. Then comes another property that is called the viscosity. So it is basically the property of the fluid, basically means it is like, you can say, the hereditary properties of the fluid. Okay, and each means that property, that viscosity, offers resistance to the movement of one layer of a fluid over another adjacent layer. Okay. Now what happens? Let me give you some insight explanation of this viscosity. Okay. Have you studied this viscosity before this? How many of you are aware of this?
Sir,
Hello, students.
I think everyone.
Yes.
Hello.
Yes, sir.
Anyone of you have any idea of that viscosity? Have you ever studied this earlier?
Yes, sir.
Yes,
In
yes,
class
sir.
Yes, sir.
stand,
11.
standard
Okay,
11th.
so basically you
Sir,
all are aware
practical
of
also, sir, there.
what?
Sir, in practical also, sir, they have taught us
There
about
was one
Okay,
viscosity.
so you
experiment.
have done practical also. Okay, so that basically, if you are aware, then it's okay, it's good. But let me explain some insight of this viscosity property. For this, let me explain this. What basically saying that means this sentence, it offers resistance to the movement of one layer of a fluid over the another adjacent layer. So I'm explaining this statement basically means how the viscosity plays this role. So look at this. This is our fluid. This is our basically the fluid which is moving towards this stationary plate. Let us take this is a stationary plate. Okay, this is a stationary plate like your table, like anything. Okay, a stationary plate means the velocity of this table is zero. That plate is totally fixed. It is totally static. Velocity is zero. And the fluid over this plate is started moving. Now what happens due to this property of this viscosity, the fluid which is just the vicinity of this plate is the fluid which will come just here at the vicinity will stop to move due to that characteristics, that viscosity, because it takes the velocity of this plate. It is considered that it takes the velocity of this plate. And what is the velocity of that plate? It is zero. And that this is the reason why you will find that the after moving of any liquid over the surface, it is wet, because the layer which is in the contact of this plate, okay, it comes to rest. It comes to rest after getting contact with this due to these properties. And the fluid which is just above this will move slightly ahead, because the velocity means the velocity, there is a velocity difference between the two layers. Fluid always flow in a layer basically. If the fluid is like a laminar flow, or in any flow, it generally flows in a layer wise like this. So this will move further ahead, this will move further ahead, this will move further ahead like this. And a distance comes here, means that distance where you will find that the velocity of this upper layer will be equal to this initial velocity. That u infinity is the initial velocity with which fluid was moving before coming to contact of the plate. So we will find that the velocity of this layer is u infinity, means that velocity, if you will plot this graph, you will find this, means this type of curve like this, this is your plate. So here this layer has the highest velocity, which is the velocity of free strain. Okay, and this layer will have the minimum. If it is in contact, then you can say it is zero. So that's why you can see here it is started from this line, just here. So at this point, that velocity is zero, because plate is zero. So this is how it offers resistance to the movement of one layer of a fluid over the adjacent layer. And this happened due to the property of this viscosity. So the viscosity of fluid is a measure of resistance to deformation. Means if a fluid has the more viscosity, it will deform less. Like here we have the two fluid. This is your honey, okay, and this is water. So you will find that the viscosity of honey is very large, and to deform means to use that honey you have to tilt, means your tilting angle should be large in comparison to water. Your water can come out from the bottle with a very small tilting angle, but like honey and any sauce, you can say like tomato, any ketchup, you will find that you need to move because they are very viscous. Okay, so more viscosity means there is a more resistance to deform. They deform very less. So this is the viscosity property, and every fluid has their own viscosity value. However small it is, means like air has a very less viscosity, but yes, there has some viscosity. Then comes a law here, which is called the Newton's law of viscosity. Okay, so basically that Newton's law basically tells that the shear stress is proportional to that velocity gradient. This is also called the deformation. Okay, with respect to y, like here, what I have plotted here, means what I have draw the diagram here. You can see this is your u velocity. Okay, this is your u velocity, means the velocity in this. If you will take this here, let me take the direction x, and this is y. So this u is the velocity in this x direction, and the gradient is developed, always gradient develop in the perpendicular direction. So look at here, that du by dy. So that du by dy means there is just some gradient. So look at here, it means if this value is not equal to 0, it means there is gradient. And yes, during the flow of fluid, there is gradient, that the gradient exists. You can see here the velocity. You can, if this is 0, so obviously this, if you will take this u1, u2, u3, u4, u5, u6, u7. So obviously, like here, u7 is greater than u6, and then u6 is greater than u5, then u5 is greater than u4, and then u4 is greater than this u3. Like this, you will move, you will go up to this u naught. Basically, this u naught, you can say it is 0 because it is in contact of the stationary plate. So it means if there is a variation in this u in the direction of y, look at here. Okay, it means that this u vary with respect to this y. In the direction of y, there is a variation in the u. So that is gradient, and due to this imbalance in the movement, in the motion, due to this imbalance, what happens? This fluid, let me take the two layers and try to understand these concepts. This is the insight of this flow of the fluid. Okay, this has the velocity u7 and this has the velocity u6. Let us try to understand what happens if this layer will try to move, and this is in contact with this layer. So it will try to resist their movement, the movement of this layer. And obviously, if it will resist, then a force will act in this direction. And if this force is parallel, so obviously this will be the shear stress, because that force will act, means you can say not the stress, means you can say the shear force. And if you are taking over that area, means for a particular area, then it will be the shear stress. Okay, so there, due to this imbalance in the fluid velocity, stress generally comes into the picture between the two different layers. So I mean to say, in every two layers, means between the two layers, there is a shear stress. Yes, their value depends on the velocity, this velocity difference, this velocity difference, this velocity difference. But yes, there is a shear stress. Okay, so this is how that shear stress comes into the picture. First of all, means the first question is how shear stress developed. So this is your phenomenon, how the shear stress developed. Now moving to this is the Newton's law of viscosity. So after knowing that yes, there is a shear stress due to the imbalance between the motion of the fluid layer, there comes a shear stress, and that shear stress on a fluid element layer is directly proportional to the rate of shear strain. So this is your shear strain. So why shear strain? Because if you will take this as a fluid layer, let us take just a fluid like in a rectangular form. So after moving, you will find that this is moving like this. So you will find that there is some angular changes you will find here, and this layer is like your upper layer, like u infinity, and this is there, you can say this is the u naught. So there exists a velocity difference, that is u minus u naught divided by, here you can say y naught minus y infinity. So there exists some value, it will be not 0. So this is your strain, because you can see here that there is some development of a strain, that theta value, that we will discuss broadly in the future lecture. But here you just need to understand that yes, there is a development of some strain, and that obviously it is a shear strain because the force acting is parallel to that all these surfaces like this. So that's why it is shear strain, and that shear strain is
Sir, you're not audible.
You're not audible, sir.
Hello students, am I audible?
Yes, sir. Now you're audible.
Okay, there was a call drop, I think. There was some interruption in the internet.
Yes,
Interruption. Let me
sir.
present this slide again. Okay, anyone can tell me what was the last line which you were able to heard from my side? What was the last line?
So you are talking about that it is directly proportional to that. Development of the shear strain.
Yes, proportional to shear stress. But actually, I repeat this line, so I've repeated so many times. So okay, all of you,
So
I
can
think.
you please explain shear stress once again, how it is developed in that liquid?
Okay. So is this screen visible? Let me repeat this. Okay, again.
Yes, sir. The screen is
Yes, sir,
visible.
visible.
Okay, if you have any question, then you can ask because we have already stopped. So let me ask if you have any uh, doubt or any query. So you can ask. Otherwise, we will move further. Are you all getting the idea, na, what I am talking with?
So development of stress, can you explain it again?
Development of stress means you want to repeat this.
Yes, sir. Shear stress.
Okay, so I am. Let me do it in this presentation mode. Okay, so development of stress basically. So development of a stress occurs due to the velocity difference basically between the fluid layer. Okay, so what happens here? I was discussing this here, how this here stress develop. Look at these two layer basically, that layer 7 and 6. What happens? Obviously layer 7 will try to move fast in comparison to this U6. and it will move some ahead in comparison to U6. And due to this, what happens that U6 layer will try to resist the motion of this U7 layer. How it will resist? It will apply a force in the opposite direction like this, and of course that force will should be parallel to this layer. So if it is parallel, so obviously it will generate a shear effect. Okay, and that force, that basically the shear stress, that means the shear force develops between the two layers, okay, due to this reason, because one layer is moving ahead of the another layer. Okay, so that layer which is lagging, from the above layer will try to resist the motion of the this, like here it is U7 layer. So during that resistance a force developed, and that force is parallel to that surface, and that's why it is called that shear force. And when we consider that force for a particular area, then it is called shear stress. Now it is clear?
Yes, sir.
Okay, so basically in one line you can say, in one line, that was the more insight. In one line you can say that the reason for the development of that shear stress is the velocity difference, because there is a velocity difference, they are not equal. And due to that viscosity property, the one layer try to resist the motion of the another layer. And obviously if there is a resistance, it means there will be some force of resistance. Okay, and that resistance is basically the property, this viscosity. So this is how the shear stress develops, and that shear stress is basically means based on this, the Newton has given that this law, which is called the Newton's law of viscosity, that shear stress is proportional to shear strain, that is velocity gradient. And when you will remove this, you will come out with a proportionality constant, that is which is called the dynamic viscosity. Okay, so this is your dynamic viscosity, which is sometimes called the coefficient of, sorry, this is S. Okay, so this is basically the dynamic viscosity. We have the two viscosity that we will discuss later. Okay, so generally this is called the coefficient of viscosity. Viscosity means that dynamic viscosity is also called the coefficient of viscosity. Okay, so this is how, means there this is sometimes called the shear strain, which I was discussing, but we have lost the connection. So what is shear strain? Because you can see here, this is, if you will take the two layer, that this is your like U6 and this is your U7. So we know that if U7 will move ahead of this 6, so when you will join this, you will find that there is some you will find this angular deformation like this theta, like here you can see here. Okay, so this is how that a deformation comes into the picture. Okay, so that's why sometimes it is called that it is shear strain. Shear is basically due to the parallel nature, because the force, that shear force, acts parallel here. Okay, so that's why it is called the shear strain. Okay, so this is your Newton's law of viscosity. Okay, now as I told you that there is two viscosity. So this is your dynamic viscosity, and then comes another viscosity, which is the kinematic viscosity, and that kinematic viscosity is defined as the ratio of dynamic viscosity to the density. So when you will take this dynamic viscosity in comparison to density, it gives the kinematic viscosity, and the unit of this is meter square per second. Okay, so this is your basically the dynamic viscosity, and the unit of this kinematic viscosity is this Newton second per meter square. In the terms of kg, you will find it is like kg meter per second. This mu, sorry, this is mu. Okay, so this is your basically the dynamic and kinematic viscosity. Now then the comes variation, because this viscosity varies with temperature. Okay, Just give me a second. Okay, I'm getting an important call actually. Okay, so now we know that this viscosity varies with temperature. Okay, so in the liquid, cohesion and momentum transfer basically. So in the case of liquid, basically that viscosity decreases as the temperature increases. And relatively it is like independent of pressure, means like it is like incompressible, you can say, because we know that the liquid is somehow incompressible in nature. But this is not the same thing which is happened to gas also. Actually gas is just opposite. Viscosity increases as temperature increases, and viscosity increases as pressure increases, because when the pressure increases, your viscosity means your the gas gets compressed, and when it is compressed, and that the viscosity increases. Okay, so these two phenomena is generally found, okay, with the viscosity, with temperature, with the variation of temperature. Also
Sir,
there is yes.
sir, how viscosity and surface tension are related?
How?
Viscosity and surface tension.
Surface tension, we have not reached the surface tension yet,
Sir, I am just asking.
and there is no actually the such need of that with surface tension basically. Okay, your actually the depend, like the, you can say the dependent independent variables is like temperatures. Okay, with means surface tension is a surface phenomenon.
Okay, sir.
Surface tension is basically a surface phenomenon. Then why there will be a significant role of this surface tension on the viscosity? Surface tension always occur, means that phenomena always occur at the surface, and fluid is contained throughout the your space, means you can say the container, if there is like pipe, like anything, then why you are thinking for this?
Sir, because
Do
sir,
not
when
ask,
I'm on a
do not ask
surface.
unnecessary question, it creates confusion.
Okay, sir.
Okay, what I was discussing, okay, yes, I was here. Okay, this graph means this is basically generally a graph for like air, how it varies with the temperature, and this is your for the like a crude oil having the specific gravity like this. So this is just for showing, means the trend. Okay, so there is nothing to means elaborate. I'm just showing means a trend, how the viscosity varies with the temperature basically, means one for a gas and one for a liquid item. So you can see from these two that how the viscosity increases and how the viscosity of this oil, basically the liquid, is decreases. Okay. Now then comes here, this is very important basically, these types of fluid. Okay, we have some, okay, we can complete this topic. The types of fluid, basically we have the different types of fluid, means there is a category of the fluid actually, and that category is depend on their behavior with respect to like the time, with respect to rate of shear, like this. Okay, in terms of, you can say in terms of viscosity or in terms of rate of shear, how they behave under the different conditions. So not all the fluids behave with the same phenomenon. There are, means all the fluids have their own behaving properties, you can say, when you are applying force, or like with the time, like this. So different fluids behave in the different manner, and that's why they have been categorized. Like ideal fluid, like real fluid, like Newtonian fluid, like non-Newtonian fluid, like ideal plastic fluid. Okay, here in the graph, okay, we will take this graph. I will have another graph also. I will show you. Okay, so this graph have some lines, basically the curve you can see. So that all the different curves shows the different behavior of that fluids, and these curves is based on these relations. What we have discussed earlier from the Newton's law of viscosity is this. Okay, so the fluid which follow this, only this, is called the Newtonian fluid. You can see here, this is your Newtonian fluid. But not all the fluid is a Newtonian fluid. The fluid which follow the Newtonian behavior is called the Newtonian fluid. Newton's law of viscosity is called the Newtonian fluid. So this is our Newton's law of viscosity. Okay, so here you can see here that stress is proportional to gradient. Just simply, there is no A term like this. Okay, what is A term, that I will explain. Okay, but this actually represent your this u du by this will be mu. Okay, like this. So that is your Newtonian fluid. Now there is a further fluids like dilatant fluid, like pseudoplastic fluid. This is also called the shear thickening fluid. Shear thickening fluid. Here it is shear thinning fluid. This is thinning, this is thickening. Okay, they both behaves in opposite manner. Okay, so dilatant is also called the shear. Here, let me show you this. The another graph. Here you will find the shear thickening and shear thinning fluid. Okay, so this is your shear thickening and shear thinning fluid. Then there comes a Bingham plastic. Then generally another, which is here you can see this is like Bingham plastic. Okay, and then plastic means all are the behave depends on the behavior, how they behave with respect to shear stress and rate of shear. You can say here also the strain, the shear strain. Okay, so means how the fluid behave under the action of force, you can say. Okay, that means that gives the criteria to define the fluids, the class of the fluids, like whether it is Newtonian, like whether it is non-Newtonian, like ideal plastic, like ideal fluid. Okay, like this. So here you can see these fluids, this and this is not following the Newtonian behavior. Then how we can find out the relations if they are not following this? Then what is the another relation? So this is your another relation. So let us take this first, Bingham plastic. Let me explain this line, basically what this line is saying. In this case you will find that n is equal to 1, because you can see here that this rate of shear is just proportional here. Okay, means the linear variation after a wild value of a stress. This you can say the wild value of stress, of shear stress. Okay, of shear stress. So this A is basically a wild value of shear stress. What this wild value says basically means the fluid which itself is not able to start the flow. It needs a initial, you can say a initial push type, means we have to give a wild value, and after that it will continue the motion. So here we need to apply external stress, and that external stress should be greater than this wild value. This means wild, you can say the wild stress. If your external stress is lower than wild stress, then motion will not come for this type of fluid. You can the example is like mud. Okay, in Hindi it is simply called like the kichad, means like this mud. So you can imagine, okay, say mud do not start their motion itself. You have to put some initial motion, means the while stress, you have to put some while stress, and then it started the motions. And after that, that follows the linear variation with rate of shear stress. Then move to the another behavior like this shear thinning and shear thickening. So that for the shear thickening means for this fluid your n is greater than 1, and for this like n is smaller than 1. Okay, so when we will put this, we will come out with this type of flow. The example is basically means for this type. Let me come out with this. Okay, so all these actually I have already discussed. Okay, the same thing is written here. Let me come discuss the shear thickening and shear thinning and shear thickening. Okay, so that shear thinning basically exhibit a proportional increase in the shear rate as a function of shear stress. Means when you will apply the shear stress, means when you will apply the shear force, okay, their shear rate, okay, the increases. Hello, kindly mute your mic. Let me give you an example. Always that paint, any paint, like the paint we use, like wall paint, like the plastic paint, any paint, exhibit this behavior, shear thinning. The paint is in the widely used example of the shear thinning. Means your paint is based on this behavior. Shear thinning means your paint should be based on this behavior. If your paint is not based on this, then it will be very difficult to paint your wall or anything, because as soon as you can imagine, if someone has used paint that brush for painting, what happens when you apply the shear stress, that their rate of deformation is increases. It means it is very easily cover the wall, and that is what it is saying, that it is that with the application of shear stress, your rate of shear is increases, and due to that behavior your wall is covered with the paint, because it has that paint has this property that their rate of deformation increases with the application of that stress. This is the reason. And just the opposite of that shear thinning, we have a shear thickening type of fluid. Here what happens when you will apply the stress, their rate of deformation started slowing like this. It means as soon as you will apply the rate of shear rate, okay, the viscosity increases like this. So this is like one of the example, like gypsum water mixture, like these glass particles. You will feel that such type of behavior in that fluid. Okay. Here are some other example of this shear thickening, like toothpaste. Because toothpaste itself, you will find that is not coming out with cover. But when you will apply some stress, it started spreading very smoothly. It means their rate of deformation increases just application of that. So these are the some examples of that shear thinning fluids which exhibits such type of characteristics. So it is called that different fluids have their different characteristics. Okay, now I am asking, there are some like this what is ideal fluid and what is real fluid. Okay, actually the ideal fluid means when the viscosity is 0. It means there will be no shear stress. It means, let me take this. If this is 0, so shear stress will be obviously 0. So this is ideal fluid, but actually such type of fluid doesn't exist in the nature. But yes, for practical or for a study purpose, we use such properties also. Like there is a different chapter in the fluid mechanics. Again, you will find a chapter which is called the potential flow. Okay, so in the potential flow, we use generally the ideal fluid, means the viscosity is 0. Okay, but yes, real fluid means the fluid which has the viscosity, means has some viscosity value, whatever the values, but there will be viscosity. So that is the real fluid actually. Okay, and anyone can tell me what this line represent? if you have studied, and anyone can tell me this line and this line. I'm just asking. It is just a common question. It is based on a simple concepts. What these two lines represent. So that actually I have already told that this is ideal fluid. If you will use your concepts at this axis, what is the value of shear stress? It will be 0. When it will be 0, obviously there will be when no gradient, means du by dy will be 0. When du by dy will be 0, when there is no velocity between the two layers, and when there will be no velocity, when there will be no resistance, and when there will be no resistance, when there will be no viscosity. Is the property which develop this. So this line represent basically the ideal fluid. This line represent ideal fluid. Now tell me what this line represent. Fast. I will stop here.
Viscosity.
What? Anyone?
Sir, solid.
Solid. That's good. So this is basically ideal solid. Now, why ideal solid? Because at this line, what is the value of du by dy?
Sir,
It
10
is
into
0.
0.
There is no gradient, but yes, there is shear stress. Means if you have a block, you are applying the force, means shear stress is there, but there is no gradient. So when it will happen? When it is a solid body, because solid body moves with the molecules at their same position. Okay, so that represents basically a solid line because there is no gradient, but still there is a stress. When you will apply the stress, there will be no gradient. So that happens basically in the solid. So this line represents the ideal solid. Now, actually,
Which is the line of ideal fluid?
What?
Ideal fluid वाली line कौन सी थी सर?
नीचे वाली बच्चा जहाँ shear stress
Exact.
0 means there will be no development of shear stress.
तो सर फिर इनका rate of shear कैसे increase होगा?
What?
सर नीचे वाली line में rate of shear is increasing. Sir, how it will increase if it is ideal fluid?
नहीं समझ में आ रही आप क्या बोल रहे हो. Actually, I am running late. आप कल पूछ लोगे? जो भी है यहीं से शुरू करेंगे.
Okay सर.
वो मे भी तब तक आप इसको देख लो, मे भी कि आपकी कंसेप्ट क्लियर हो जाए. ओके.
Okay सर.
ओके. आई एम चेंजिंग ऑल द डिस्कार्ड्स. ओके, आप इसको करो. ये आप अगर किसी भी बुक्स में जाओगे तो आपको ये भी मिल जाएगी, ऐसी कोई बात नहीं. बट लेट मी टेक द अटेंडेंस बिकॉज इट इज ऑलरेडी.
So also, so could you share the PPT?
Yes, I told you yesterday that after covering
Yes,
some
sir.
part, I will already. I will share. I will share
Yes,
by my. I will share all the lectures notes on the Google Classroom for your kind information. Okay. After covering,
Thank you, sir.
like let us 2 or 3, you can say, or like after completion of one chapter, you can say. Okay. I will share the lecture notes. So don't worry about this that I will not share. Okay. I always share with the students.
Okay, thank you, sir.
Okay, now we are running late actually. Okay, so let me take the attendance first, and whatever your queries we will discuss tomorrow. Kindly note your queries. Okay.
Okay, sir.
Okay, yes. Roll number 1 is present. Village. then Abhishek Zangir, then Abhishek Kumar 3, then 4, Adarsh Pandey, Ajay Bharti, Ajit Singh, Akash, Amandeep, Amandeep no, Amar Bhardwaj, Amit Kumar, Anand Jain, Aniket, Anirudh, Anjali, Ankit Anand, Archit, Arjun, Ashpit, Aryan, Dwivedi, Arya, Asis, Meena, Asutosh, Atul, Ayushi, Chaitanya, Charan, David, Deepak Nan, Apo, Deepak, Deepak Nan, Deep Nan, no? Okay, he is absent. Aniket, Aniket.
Yes, sir, present.
Okay, you
Yes,
are
sir.
present. Okay. Dev, Devasis, Satvik, Gagandeep, Gaurav, Geetika, Gurmukh, Harish, Har, Harneet Singh, absent. Okay.
Present, sir. I'm present.
What? Harneet Singh. Bachap. Okay, Harneet Singh. Harsh Bajaj. Harsh Bajaj? No. Harshit, Hemant, Joshi, Himani, Inayat is present. Ishu is present. JV Reddy, Karanveer, Satish, Harish, Lokesh, Manisha, Manshul, Muhammad Danish. Danish Alam? No? Okay. Mohit, Naman Gupta, Narendra? No. Naresh, Navdeep, Neeraj, Nikhil, Nikhil, Nikhil Kumar, no? Okay. Nikita present, Nilesh present, Nitesh present, or Nitesh Singh Solanki present. Om Shiv present, Vinay Babu present, Pratibha, hello. Pratibha, no. Radha Mohan is present, Raghavendra is present, Rahul is present, Rahul Kumawat, Razan, Ramanpreet, Raminderdeep, Ratanas, Rayan Ali, no? Okay. Rishabh Kumar. And where is Rishabh Sharma? Okay, Rishabh Kumar, Rishabh Sharma present. Yes, okay. Rohan, Sagar, Sahil, Saksham, Samir, no. Sandeep, yes. Saurabh, Shalu, Shivam Goyal, Sri Harshita, Sri